must be larger than 0. J cannot be negative. J cannot be 0. Because J, if J, the cost index cannot be 0, cannot be less than 0, has to be larger than 0. Because of that, if I have this constraint, if I require Q larger or equal to 0 and R larger than 0, that means J will never be negative. True? What is the definition of positive definite? Definition of positive definite means U transpose RU must be larger than 0, right? So if I have one term, this term has larger than 0, then another term can be 0. Then you might ask, why I cannot use Q larger than 0 and R larger or equal to 0? Any reason about that? Any reason about that? Why we have to have this way? We cannot have another way. See, in my final, I say, okay, J can be negative. True or false? False. See, this is a concept there. I talk about the concept in the class. Listen carefully. J cannot be negative. And R has to be positive, definitely. R must be larger than 0. You can go back to read the, if you look at carefully about this, go back, this, can R be 0? This, can R be 0? No. See, so from this single degree of freedom give you a lot of hint. Here, R cannot be 0 because they are divided term here. Understand now? Okay. Now we can prove that later anyway. So, but I just show you the okay. Now, this is definition. What is the optimal control? The optimal control means giving a system x dot equal to ACX plus BCU with the four-state feedback. The four-state feedback U equal to FCX. X is a four-state feedback. And if that FC minimize the cost index defined like this, J equal to half integral from 0 to infinity, then parenthesis X transpose QX plus U transpose RU parenthesis DT. If I minimize that J, means my FC is the gain of a optimal control design. That's all. So this is the definition of optimal control. If I look at this, X dot equal to ACX plus BCU and U equal to FCX. However, again, if I minimize this cost index, then it's optimal control. If I don't minimize this cost index, I just use Paul President technique to compute a FC, then that's not optimal control. Okay, that's not the way of optimal control. All right, the key equations. This will be more complicated because now we are all matrices. AC is a matrix, BC is a matrix, FC is a matrix, and so on. And the cost index, you will put in the cost index there. Then the XTQX plus UTRU, then the Q, then U equal to FCX. So in here we sub U equal to FCX in it. Then I got a Q plus FCT R FC X dt, and then if I sub this X into it, then I have these equations. I got that equation. How can I solve that equation? Very complicated, right? It's not scalar. If scalar is easy to solve. I solved it already for the 1 degree free. Now this is a matrix, but in matter of fact, you can solve the same way. So if you understand the scalar problem, that's why I introduced the scalar problem first, and then look at the non-scalar problem. This is non-scalar problem. So you have multiple degree freedoms. Now let us introduce a matrix called P. P. Now P is the term. This is the matrix you really get from your optimal control. Now, if I have a P satisfy this, that's my P satisfy that. Look at this. It's quite complicated. I will show you that there's a problem to solve this kind of P. If you know AC, you know BC are given. If you have an FC given, we don't know FC. If AC plus BC and FC, in other words, I have a system that AC, BC is given. Assume. Here is, we assume that we have a P satisfy these equations. Okay? Let's assume. And this is our matrix. That's our matrix. Now for our system, X dot equal to ACX plus BCU, right? And my U equal to FCX. Okay? My index is, J index is, that's X transpose QX plus U transpose RU, and then dt. Okay, so we now have giving, all right, giving AC, we know AC, the system BC, we also given Q, and giving R, and we know Q has to be not equal to than 0, and R has to be positive definite. So given AC, BC, Q, and R, now we want to solve FC such that partial FC, partial J equal to 0. That's what we want to do, right? Right? That's what we want to do. Agree? But now FC is a matrix. What can we do about the matrix? And what does that mean, partial J, partial FC? This is scalar. This is scalar. And we know that this J has to be larger than 0. Right? Okay. Now what does that mean, partial J, partial FC? That means partial J, partial each element in FC must be 0. For example, my FC equal to, say, we have a single input problem, then the FC will be we have a single input problem, then FC will be, say, F1, F2, to Fn. That's a number state. Okay. That's a single input. Then partial J, partial F, partial J, partial F, C, that means partial F1, well, that means partial F1, partial J, partial F2, partial J, and so on, partial Fn, partial J, then it has to all equal to 0. Okay? Now, to be able to solve this, we are not going to solve this like this. We're solving it a different way. Alright? Now, if there exists a constant symmetric matrix P such that the following equation is satisfied, my solution FC is here. Assume that is true. Okay. Be careful. This is the key equation. If that's the case, then I can dt, and I have exponential AC plus BC FC parenthesis t, then parenthesis minus t, then e to AC plus BC FC, and so on. Now, if I submit that p, because if you look at carefully here, dt d that means I differentiate this term, that means that term, and parenthesis AC plus BC FC t, and minus p here times this. Plus I differentiate this term, then I get that term. Alright? Now here you gotta be careful here. There's a mathematical problem here. I need to explain it a little bit so you understand better. Here. Alright, now assume say A C bar equal to AC plus BC FC, right? Then dt, the exponential AC t equal to, we know that this is AC, then exponential AC bar t, right? Or equal to exponential AC t AC. Agree? Differentiate exponential term, matrix term, equal to that, or that. Right? You agree or not? Now, a matrix, we know that AB won't be equal to BA if this is BA. Right? Agree? For a matrix. But when AB equal to BA, when? Don't forget, huh?